everybody. And first I would like to thank the organizing committee for just gathering all of us here and also for giving me the opportunity to speak here. And so just my topic will be a very old one, actually, maybe with some comments on current state of it. I'll speak about Petri nets, and in some sense it was inspired by the case that many people, of course, so most of people have heard that there are Petri nets. They know that they are used for modeling, but they didn't have an opportunity to understand what exactly are Petri nets. And then I'm trying to give, of course, short, and I would say soft introduction to Petri net so that you can understand whether you do need to read more or not. So, So, I can say that I'm from Moscow High School of Economics, computer science faculty, and we have a laboratory of process-aware information systems. Чем? So I suppose that you know what is a finite automata or finite state machine. And so just here you see, just two finite state machines. So just each has two states. Yeah. Okay. And you see they represent, so the first represents a sender, which can send a request and then receive acknowledgement, and receiver who behaves symmetrically. And usually, of course, finite state machines are used for representing languages and compilers and all this stuff, you know. But also, they are very good for representing behavior. And when we speak about reactive systems, which is the case with the sender and receiver, then the normal case is infinite behavior. So here we have initial states not designated here, sorry, but we do not have final states. And we consider so-called infinite runs, so infinite sequences of states and transitions, which represents the behavior. So here, of course, it's a trivial case. We have deterministic automata, and we have just one line infinite behavior, and it's not very interesting. But the interesting question is that when we have distributed system, then, of course, we have distributed automata. And then, when we look, we would like to describe interaction of this automata. Then you see the trick, so just transitions were added on arcs. In finite state machine, an arc is a transition, but we do not, we should put a label. But here we have implicit designation of transitions, and we have T1 and T2, you see, yes? And then now, with this small trick, we can draw a system which has synchronous interaction. So just two actions are done simultaneously. What has changed actually when we look at this model, which is visually very clear, I hope? So just the difference is that, so just for finite state machine, so always current state is represented by a graph node. But here, so current states, we should show what is the current state of left automata and what is the current state of right automata. So we add tokens to designate active states, you see? So now we have quite a different thing. So now our states, so like we have drawn transitions, we can draw a tokens, just to put it to designate where we are now. But for this case, we do need several tokens. Then the next trick, so also these two agents can interact asynchronously. That means that there is a kind of channel for sending messages and sending acknowledgements. So we designate it also. You have noticed, I guess, that we have here two kinds of nodes. We have circles, which designate states, and we have squares, which designate actions, transitions. And now, so we add also, so states, they are not states, they are called places in Petri nets. And so they may also contain tokens, but now the meaning of this token will be some kind of resources, which is maybe consumed by a transition or produced by a transition. So now we have another example of it. It's also a Petri net. And what is the difference here? So as well as in synchronous case, in finite state machine, we have always one ingoing arc and one outgoing arc for each transition, but here we may have several. And then, so just actually, this was a very short, so just introduction to give you some intuition how to look at Petri nets. But of course, both these cases are very restricted, and in general case, when we have, you see, graph with two kinds of nodes, places, which are local states of the system, and transitions, which represent actions, then we can have very different and more complex situation. So, and this kind of formalism is called Petri net, and Petri is a name, and Carl Adam Petri, so just one of the prominent computer scientists of 20th century, because he did really very much for modeling distributed systems, so which we are aware of. So, and he called it communication automata as well. But of course, now it is much more general concept than, and it was, as he introduced it, then just communicating automata. So, what is a Petri net and why it is so popular? So it is a formalism which allows us to model and analysis asynchronous, generally speaking, systems, distributed, parallel, non-deterministic, also stochastic systems. And it is very important that similar to finite state machines, it is both very clear visually and it has a very precise mathematical semantics which allows us to make formal analysis for such models. So, speaking about design principles, we have places, as I told. We have transitions. Places may represent local states also resources, also conditions. And you see what is important. Now we have here two tokens in one place. What does it mean? If we have some resources, then it may be not just that we have a needed resource or don't, but how many resources do we have? And then you'll see an example. It can be that a place contains several tokens. And so I'll tell it also a bit later once more, but the immediate consequence is that it is not a finite state now, formalism. So just the number of reachable states may be infinite. And transitions represent actions, or we are interested in describing behavior in terms of these actions. And also, of course, there are arcs which link transitions with action, transitions with places and places with transitions. So we can't, just syntactical restriction, but with very natural meaning, we can't connect a place with a place directly, because just this connection should describe behavior changes. And so places are passive elements, but we do need some action to change something in the place. And the same for transitions, just they are connected with different kinds of channels for sending signals, for sending resources, and so on. So correct case would be that two transitions have a place in between, and so it may represent a channel, for instance. Then, to summarize, it is a bipartite graph, yeah? And we have two kinds of nodes for local states, places, and for transitions. And we have flow relation. Also, since now a place may contain more than one token, also it can be that a transition consumes more than one token from one place and also produces more than one token into another place, and that we have weight functions for arcs, and we have so-called initial marking. So marking is a synonymous for state here, so marking represents states, and marking means that we just put tokens to some places. So we start with initial marking, which is a function mapping each place to some natural number, including 0. 0 means no tokens, and natural numbers, so n means n tokens in this place. Now, of course, this was just some syntactical aspect, but we are interested in behavior. I'll skip for now this slide definition, but show you an example. So there is a story, I don't know whether true or not, that Petri invented his notation at that time when he was a schoolboy, and when he was studying chemistry, and then he needed to draw something to understand chemical reaction. So he invented this notation and then used it in communication automata. That's why we have this example. And what do we have? So we have a transition, which is a chemical reaction, and there are several places which have arcs going from places to this transition. They are called input places for this transition. And we have two input places corresponding to resources needed for this reaction. So that is oxygen and hydrogen. And then also there is one output places when there is an arc from transition to this place, and so it is labeled with water. And also we have, you see, labels on arcs. So they show the multiplicity of tokens consumed or produced by this transition. So just for chemical reaction, so we do need 2 molecules of hydrogen, 1 of oxygen, and we get 2 molecules of water. So this is a result of transition firing. So it is very important that it is not like a game of moving tokens. So the number of tokens may change. Yeah? So it is, we just represent some resources of this or that kind. And so here, so uppercase, we have a marking before firing of transition, and the lowercase is a new marking after this transition firing. So now we can return to the definition, and we then can say that so a transition is, they call enabled or can fire if it has enough resources for firing in all input places. And after firing, so just we have, you see, so this inequality. And after firing, we have, so just we should compute, so minus all consumed tokens and plus all produced by this transition. So I would tell that since there will be maybe too much or information for some listeners and maybe nothing new for another, but still, so just you can interrupt me and ask questions at any point. Yeah. So you have this example. So, of course, a finite state machine is a special case of a Petri net, restricted case. And so here is an example. It is a vending machine. It is a finite state automata, which shows, so just there are different passes, different runs, which correspond to different, so just we need to pay for a candy. There are 2 kinds of candy, and there are several variants of coins available, so we can pay with different sets of coins for these candies. So just, I think it is quite clear. And then, of course, so just for finite state machine, we just have arcs connecting so states of this finite state machine. But here we have also transitions. So just how much do we pay? So then, of course, finite state machine is a Petri net, very special. What can we model with Petri net? So, of course, we can model choice, like in finite state machine. It will be non-deterministic choice. Also, so contrary to finite state machine, we can model concurrency. So here we have a situation if, so just initially we had a token in phi5 and then T1 had fired, then we get a marking which is shown here. So now it means like to have a fork after which we have 2 processes running concurrently. So we have a token in T1, that means that T2 can fire. And we have a token in P2, which means that T3 can fire. So they can fire independently. That's concurrency. And then, so just you see, then we can split it. Join these 2 passes in one, 2 spreads in one. Also, sorry. Yes, yes. So that was I was too quick. So of course we can model different kinds of protocols. Actually, classical Petri nets are extremely good for protocols because we can model control flow and all kind of interaction. And here we have 2 processes, send and receiver, each runs its own cycle, infinitely long, and from time to time, a sender sends an item to receiver, and receiver sends an acknowledgement via another buffer, and then so of course what can happen, not here, that here we can't send anything else before, so we have an acknowledgement. Yes? That means that the number of tokens in our buffer is restricted to one. Such system is called safe. So just we do not have more than one token in each place, in all reachable states. But sometimes there, so of course, you know, in reality, and also in Petri nets, there may be an overflow. This is one more example showing data flow computation with Petri nets. So just it is, of course, here we have just a flow, but with concurrence. And now, so just what I was telling before was how a transition can fire. It was called firing rule. But what is actually the behavior of such systems? So how these steps, transition firing, can be combined. So like in many formalisms for distributed concurrent systems, there are several kinds of semantics. So one way to represent concurrency is interleaving or sequential semantics. What is it? It means that, so just if, for instance, two actions are run concurrently, A and B, are done concurrently, then we can understand it like, so first it was A and then it was B. Or first it was B and then it was A. It looks a bit strange because of, so just it was concurrent, but now we made it sequential. But imagine that you have a huge net, you have two actions independent, you can't know which one was the first, actually. And what is important, when you would like to analyze all reachable state, you may have all these kinds of intermediate states. Either it was that A has fired, and then only after that B has fired, or vice versa. So this is easier than just reasoning about concurrency. But what is important, with this kind of semantics, all properties which are true for reachable states in the interleaving semantics are also true in the concurrent semantics. It is called true concurrency. So then we can represent a behavior of our system as a sequential run. So it is shown here. So this is just a deterministic behavior, so nothing interesting. Actually, we can add a resource. Here, you see, so just AD is a marquee. So it represents that we have a token in A and a token in D. Then small a fires, and we come to a token in B and a token in D, and so on. This is more interesting. This is a system with two such processes which share a resource. And then if we draw into so sequential rounds, we may have infinitely many sequential runs of this kind. Although this system is safe, the number of sequential runs is infinite. If we would like to prove something for this system, then it should be like, so just for each sequential run, we have this and this property. But what is actually nice and could be expected, since the number of reachable states is bounded, so it is finite. We can draw so-called reachability graph, which is a transition system, so a graph, where each node represents a reachable marking, and transition is firing of a transition between this marking. And here we have a finite graph. And what is a run? A run, so we start from the initial state, and then we have any infinite path. Each infinite path in this graph, which starts in the initial state, represents a run of the system. So we have a compact representation in this case. Of course, it is not always so nice, because it could be that the reachability set, so set of reachable marking, is infinite. In this case, we have infinite graph, and then we have all problems connected with this, but it's also a typical case. I'll speak about this, so next time when we'll speak about properties of Petri nets. Here we speak about semantics. So we have this sequential semantics I explained. But sometimes we are interested in representing concurrency explicitly. For some properties it is important, for some for representing, in some case, real behavior, it is important. So how to represent concurrent behavior? Then there is a notion of concurrent run. What do we have? It is a graph. It is constructed just by unfolding of Petri nets. It is also a Petri net. You can notice that we have two kinds of nodes, and this rule that each arc connects a place with a transition or a transition with place. Looking at the very left nodes, you see ADE. ADE is the initial marking. Initially, we have a state with resources 1A, 1D, and Y and E. Then, what can fire? So, A can fire, and we draw firing A. Now it is like historical firing. And we come to B. After that, small b can fire, but d can fire independently, you see. So then, of course, it will be also an infinite run, but now represented as a concurrent flow. And this definition can be used for proving properties, reasoning about behavior of such system, and we do see concurrency explicitly. Of course, here we have just one concurrent run. You could say, and how many concurrent runs, so just can we have for this concrete primitive system? So the answer would be infinitely many. Actually, because we distinguish different story with these two resources. So just imagine that interpretation is that we have two processes, which two computer scientists, which share one printer. Then, so just we draw the story, how they were using this printer. And it could be that, so the first one was using it 2 times, and then the second one 1, and then the first one 5, and so on, you see? And we have each sequence, infinite sequence of such natural numbers will represent different behaviors. So, of course, there are infinitely many behaviors. The interesting question, can we fold them somehow together? Yeah, I show you, since this is a very simple system with very clear behavior, so we could guess that there should be some ways to represent it in a compact way. and it is the case. So many concurrent runs, I've told you already. So just when we look at these runs, we can notice, so you see, so the upper run, ADE. So what is the marking here? The initial marking, and then, so just each so-called cut, we have a flow. Cut represents a reachable marking. What is a cut? It contains places which are incomparable. So no causality relations between them. And then, so just here we have fragments which represent behavior, so just starting from ADE and also ending in ADE. So we can regularly insert any number of such fragments and generate a new run. Actually, this behavior is generated just by these two fragments called scenarios. And the first one corresponds, the first computer scientist was using a print and the second for the second. So just as it should be. Of course, it is not the case that we can always have such nice and compact and regular representation of the behavior. Yes, so just these are scenarios I've explained you. So just summarizing about semantics of classical Petri nets. So we may have either sequential runs, which also represent, so it is called interleaving semantics. Concurrent runs, which correspond to so-called true concurrency semantic. Note that, so these terms are not only for Petri nets, so just for process algebra, for instance, which are also used for representing concurrent systems. Another formalism, we also may consider sequential behavior, interleaving or true concurrency, everything. And also parallel semantics sometimes is useful, but not so often. It is when we synchronously fire several transitions. If we have enough resources to fire, for instance, 2 transitions in one step, we can do it. But this is for more specific, mostly for hardware, this semantics. No, so for software, more appropriate are sequential and concurrent semantics. So this was about semantics, briefly. And then, of course, what is the specifics of classical Petri nets? Like finite state automata, they are very low level. So you have just, if it is a complex system, then you have a huge graph. And then, so just it is very difficult just to understand what is it all about. That's one point. Another point is, of course, that we would like to add some more facilities to it. And here also, maybe I should tell it here. So one more interesting question is, so of course, we would like to construct a model to make some analysis of its behavior. So if we have a finite state machine, then so just we are lucky, everything is decidable. Yeah, so because we have finite graph representing the behavior of this finite state machine. If we have a Petri net, then the number of reachable states may be infinite. So it's a question whether still we have some decidable properties or we just get Turing power. And a good news is that many properties are decidable for Petri nets. For instance, reachability problem, which means that we would like to check whether a given state is reachable from the initial one. I would add that so this problem was open for more than 10 years. But now people know that, so yes, it is decidable. Also, of course, different kinds of deadlock, or also a very important property, whether a net is bounded or not, so or in other terms, whether the number of reachable states is finite or not. It is also decidable. That's very important for verification. So, and now, today I will not speak about properties, but I will speak about expressibility. What can we express with Petri nets? And so we have this basic formalism, and then there are different kinds of extensions. Of course, there are several variants of time extension, which are important. We have also timed automata. We have some time extensions for process algebra, so it's typical. Semantics becomes difficult, really. I will not speak about this, so I feel that I will not have time for this. Then, also there are extensions when we add data, because in classical Petri nets we just have tokens representing local states. We abstract from data. We look only on action filing. Can we add data? Not for modeling any kind of computation. So Petri nets are not for computation, so just to say functional semantics of programs. Yes, so there are other formalisms, horse logic, different kinds of the extensions, but data may be important for transition filing, so just conditions for actions. That's important. And also, we'll speak about extensions of Petri nets when we can model more complex structure and actually dynamic structure. Multi-agent systems are important nowadays. We do have components everywhere, interacting agents or components or objects in different applications. They have different names, but the point is that even if we can model them with plain systems, these models will be unreadable, unclear, and so just very complex for analysis. So, and of course there are some old extensions, so just we can add inhibitor arc. What does it mean? So just we can inhibit transition filing if there is a token. So just to mention, by adding this arc, we get Turing power immediately. The point is that they allow us to check whether a place is empty or not. And specifics of Petri net, which is important for decidability also, is that they are in some sense monotonic. That means that so just if we have more resources, we still can do everything we could do before. Yep. So just there are inhibitor arcs and there are reset arcs which just allow us to empty the place. So just they are intermediate. It is not Turing power. There are some very interesting intermediate classes which are between classical Petri nets and Turing power, and recent arcs are the case. So, as I told, I skip time. It is too much will be for one and stochastic. I'll go to another kind of extensions. And since I don't want, and so just I actually do not have a possibility to give all kinds of formal definitions, I'll just illustrate it by one example. So you see a Petri net which models, so just our typical work of researchers, when so just here black tokens represent researchers which may be either at home or at work. And so just, and each of them can go along this cycle. You see that there are 3 researchers in this system. At the initial state says that 2 are at home and 1 is at work. And then, so just there is another transition, which is discussion. And discussion to fire, there should be 2 researchers at work. Because there are, you see 2 arrows, or I could put 2. Yes. And also these arrows are both directions. That means that, so just to fire it, we do need 2 tokens, 2 researchers, but they are still at work after discussion. Yes? And the result of this discussion is a new project. So we gathered them in the special place. And then you see it is an unbounded Petri net because the number of projects is unbounded. So you see the system with infinite behavior and in some sense our typical life. Yeah? But now we make it more concrete, we extend it. So we would like to have not just black tokens for researchers, which is unpolite, but we give them names. So now there are researchers A, B, and C. So now I'm going to introduce an extension of classical Petri net introduced by Jensen, which is called colored Petri nets. So now tokens are of different types, and we can call them colors or color indifferent. And then, so just what else have changed? You see, now, when a transition fires, it can consume one of these tokens, but we may designate what kind. You see, we have variables now. It is a high-level Petri net. Here, when a transition fires, so just what happens? So it's just how to look. Please look at T1. So input place is P1. And for firing, it needs 1 token. Which one? So just this, we do a binding of this variable. That means that we can bind X with, here in this example, either A or B or C. For each binding, we can check whether a transition is enabled or not. For binding, when X is equal to A, it is enabled, because we do have A. Or B, it is enabled. For C, it is not enabled. So actually, it represents a bunch of transition firing. We could draw it, unfold it into classical Petri net, where we have separate transition for A, separate transition for B, could follow the story. And also then, so just X on the output arc means that, so now what will be put in P2, the same as was consumed, because so just we have assigned X to, say, A. And then A will be moved along this. What is important? So just the scope of variable is, so the scope of transition. So actually, this X from P1 to T1 and T1 to P2, it is important that it is the same variable. But I could draw, for instance, Y for the lower line, because it does work. So we have this situation now. also, you see, we have X and Y, which means that they may be different. They may be the same as well. Here we do not have the case. And projects, so just that may be a special type for project. Of course, with this high level, with variables like in logic, of course, we should care about type correspondence, all this stuff, but I guess that intuitively it is clear, and we have a possibility to fold large Petri net into a smaller one to represent the behavior. For instance, for this famous example of dining philosophers, if you draw it explicitly, you draw, so just for behavior of, to say, 5 philosophers. But if you fold it into colored Petri net, you just have a behavior of 1 philosopher and types on several philosophers. And if you want to switch from 5 to 7, you do not need to construct a new Petri net, but just add tokens. That's very good. Just to note, if we have finite colors, of course, finite number of colors, but also just each type has finite number of values, then we can always unfold it to classical Petri net. In real CPN, there is a CPN tool supporting it. So it is also allowed to consider natural numbers. So if we have natural numbers, of course, we get Turing power. One more remark. Here, of course, these tokens are just atomic tokens, maybe of different types. But in colored Petri nets, they can carry actually data. We can have a record as a token, and then or, of course, in concrete CPN, it is restricted, but we can extend it, putting there, so just a complex type, and then it will be any kind of concrete data. What for do we need data? We can add guards on transitions, which means that, so we check whether this condition is true. If it is true, for this or that binding assignment for variables, then we can fire transition. If not, it is not allowed. Each time, so just when we simulate a Petri net, we mark transitions with the assignment which can fire, and then non-deterministically choose the next one. Yeah? And also, on the output arcs, we can put expressions, we can compute new values for these tokens. Then it will be a much richer model with data, and this data will be local data, so each token carries the data. Yeah? Then, and now the next extension. Yes, I speak now. So then, just to mention, you see, so just the next extension, when we put Petri nets inside places, so they are agents. So we have had these researchers who were just had names and know to say personal behavior, but now they have personal behavior. And some steps they can do independently. Some steps can be done by a system ignoring their state, just not changing it. And some steps are synchronous steps. So they can be done only when both, so an actor and the system is ready to do it. This will be a so-called vertical synchronization. Also, we can organize synchronization of net tokens inside white plates. This model is called nested Petri nets. Here also tokens are local. And we have this, so just it's interesting that this model is not Turing power. We still have decidable properties. But there is another interpretation, so just, I'm sorry, I just would, can't show you details, how it fires, so on. But I'll show you one more thing, that for these nets within nets, net tokens, there are also two kinds of semantics. One is, as I showed you, it is called local semantics, but another possibility is reference semantics. That means that a token is not a net, but a reference to a net. And then we may have several references in the system to one object. And for some systems, it is the case when we need to model some things. And here, just is an example showing, you see this fork situation. And if we have here a token and we have reference semantics, when we fire, what happens? Now, so we have this fork, and after firing, we have two references to the same object. So it means
new object of the same class. It's the same object.
The same object, just the same object, real object. And that means that, for instance, if T2 fires, then it may change the state of this object, and then so just a reference now, so a side effect as it exists in real programming. It's not so nice, we get Turing power immediately, but we do need these for some applications, so just we do have such systems. And with local semantics, we have that in this fork situation, we have two copies of it. Yes, and also we'll speak, and Andrei will speak about an extension where so just we have reference semantics for data. Also, sometimes it is really interesting, and actually the case of London Craig's system has so just we do need reference semantics for data because we have a shared database and agents working with it. So then I stop. Of course, I
Thank you very much.